faster than normal because we had to go on. Alright, so the example I'm going to be presenting here is entity resolution. And the first question, of course, is what's entity resolution? So this is a very common type of problem that we try to solve. And entity resolution comes in various different varieties. At its core, this is about giving different references or mentions of entities and trying to resolve them down to the same core entity. If you want, you could maybe think of this as a clustering problem. This is a very common problem in, say, like natural language processing, where you're trying to do named entity recognition, things like that. So entity resolution is a very broad category of problems. And the three variants that you typically see: one, record linkage, where you have two either fully or mostly deduplicated data sources, and you're trying to match one between one record and one and another. The other one, let's say we have LinkedIn and Facebook data. Somehow we miraculously got that data. And we wanted to see who is the same people in these two social networks. That would be something like record linkage. Then we have deduplication, where you kind of have a big cloud of all these references, and we're trying to figure out, in this abstract space, which references refer to the same entity. And then the final one, kind of a match of the two, reference matching, where we have both a deduplicated data source and some sort of like rough data source, and we want to match everyone in the rough or noisy data source back to our key reference. So in general, it looks like that. PSL example, same repositories, use the entity resolution directory. That's about it. So let's go ahead and real quick, so we can get started, let me go ahead and start a run. Oops, not showing you. There we go. So I'm just going to go ahead and start a run, we can talk about it. This example is a little larger than the other one, so it's going to take a little longer to run. So the problem we're looking at for this one is specifically, we're trying to do entity resolution inside of a citation network. So we have different instances of authors authoring a paper, and we want to figure out who are the same authors and what are the same papers. So this is an interesting one in that we both have to deduplicate the authors and the papers. The data itself comes from CiteSeer, and it comes in several different variations, small, medium, and large. We're going to be working with the medium in this example. And you can kind of see a little indication of the data over there. Like, let's say we have two papers. We have Federalist number 1, Federalist number 2. Federalist number 1, authored by James M. and Klubis, and the Federalist number 10, authored by Klubis and Madison, J. Now, if you don't know, each Federalist paper was actually only authored by one author, but this is not a history lesson, this is an anti-resolution lesson. So the data looks something like this. And you can see, if we're going to start to build a model off it, we don't actually have that much data. Really, the only data we have is the author name, the paper title, and what reference of an author authored what paper. So we don't have really anything besides that to go off of. Not a whole lot. But we can imagine we might be able to put up some sort of diagram like this, where we have some papers. We know some people authored some papers. Those are hard links. We're sure about those. But then besides that, we don't have that much. We could say, well, maybe we could try and take some sort of name similarity between the authors. A really common type of name similarity is Jara Winkler. That's really common for names. So maybe between all the author names, we'll take the Jara Winkler similarity between them. And then maybe between the paper titles, we'll do a more generic string similarity. Maybe Levenstein. You could put in whatever specific implementation of edit distance you want. Doesn't really matter. So we're going to have something that looks like this. And our initial rules are going to be really simple. We're going to have rules like this. So we're going to have author name A1, N1, author name A2, N2. All we're doing is collecting the names for the authors. And we're really just saying, if those names are similar, that's evidence that they're the same author. And then we're going to do the same thing with paper titles. If the paper titles are similar, that's evidence that the papers are the same as well. So, pretty basic. Let's go ahead and see how our model did. So it ran, and you can see, of course, a bunch of output, and one thing is you see it was doing evaluation for both the same paper and the same author. So for this example, we're going to focus in on the same author, because that's usually what we care about a bit more, resolving the authors to be the same. And you can see we got an F1 of about 0.7995, so about 0.8. That's pretty decent, nothing too bad, but of course, as machine learning, we always want to be doing better. Let's take a real quick look at the full model. much the same rules I talked about before, but a couple additional ones. Here, negative priors, we've talked about that before. Here, the only difference is we have a couple hard constraints, and this is an artifact of the data that we see. The data that Sites here gave us includes self-references. So it says like author James Madison and James Madison are the same person. So in the data they had, they said same references mean same person. Sure, why not? So all we're doing is instead of kind of having to parse through our data and take those out or something, we're just encoding that as a rule. If we're looking at the same author for A and A, the exact same variable, they're the same author. Just let it be one. No big surprise there. So the rules are pretty straightforward, especially based on the ones you've seen thus far. So, of course, like I said, one thing we should always be asking ourselves, oops, don't look at that, is can we do better? In this model, we are not really yet using any kind of relational information to strengthen our model. We're kind of just using, oh, do they have the same name? That's really shallow. So can anyone think of any other things you could do to improve your model? Any other maybe perhaps relational information that we can take advantage of? And if you wanted to, you can cheat and remember what I accidentally showed you earlier and use that. What do you think?
A set similarity of the author's links to their papers?
Oh, sure. Using a set similarity of authors to papers. So maybe what you do is are you looking at perhaps all the co-authors on a paper and looking if the set of co-authors is similar?
No, I was just imagining the two separate authors.
Mm-hmm.
And how big of an overlap do they have to their citations?
So one trait of this problem is that we, for each, like what we actually have for each kind of author reference is we know an author mention or an author reference some mention of a paper. And that's kind of weird because we don't have, like what we're trying to resolve is into the same entity of an author. So we don't really have any construct that represents all of the same author yet. But we could try to encode that somewhere in rules. So that one's a little more difficult, but it is possible. Can anyone think maybe something a little more simple?
Do we have
Affiliation? Unfortunately, we don't have affiliation. I know we're pretty sparse on the data. All we really have is name titles. Does anyone else maybe want to, since we got to keep moving, maybe one of the links members want to actually just give me the answer?
Transitive rule?
Sure. So transitive equality. So transitive rules or transitive relational rules comes in several different flavors. But one of the most common ones to us, or ones we're most familiar with, is transitive equality, or a triangle closure. So what we could say is, oh, we have an author, Adam Smith, we have an author, AS, and if Adam Smith is the same as AS, and A Smith is the same as Adam, S, or sorry, Smith, A, then Adam Smith is probably the same as A. Like, use kind of really standard transitive relationship. And yes, I know Adam Smith is an economist, not a founding father, but don't worry about it. So that's something that is very natural, and it's something that kind of has been ingrained in us since, second grade math. I don't actually know the young math levels, but we've known about this sort of relationship very early. It's something that is very natural for us to want. And something very interesting in PSL is that we're not going to use this straight relationship where we have two observed links and we want to complete the triangle with one unobserved link. Instead, in PSL, we're going to say all of these links are kind of non-constant. We can infer the same author between all the edges of our triangle at the same time. So that's a lot more expressive in that we don't have to observe two links of the triangle. We can have unobserved all of the links of the triangle, or all the edges of the triangle, and infer them all at the same time. So that's a very natural rule to want. Let's go ahead and include this rule. Oh, if I can copy it right. So let's go ahead and put this rule in our model. Oops. There we go. So let's go ahead and just plop it in right here. Something like this. So the same author, A1, A2, same author, A2, A3, then same author, A1, A3. And you'll notice some extra inequality things there. Depending on your data, you may or may not use those, but we can be safe. We can just put those in there to make sure those variables are not equal to the actual same thing. So we'll include something like this, and we'll go ahead and run it. And my connection was a bit spotty, so I'm going to run it in a screen just in case we lose our connection. Let's go ahead and run it, and while we're waiting, let's go ahead and go back to here and think, is there anything else we can do? Knowing kind of, with the knowledge of kind of how we put in that transitive rule, can anyone think of any other transitive ones you might want to add, or any sort of these relational rules you might want to add?
Well, the symmetry rule is missing, isn't it? Oh, sorry, symmetry rule is missing, isn't it?
Sure, symmetry. If A is the same as B, then B is the same as A. That's definitely one we can put in. Sure? Any other ones you can think of? Like, I know it's hard because I already have the rules in my slides, and you want to try and guess the rules I have in my slides. But we'll try. I'll give you one, and there's another one. So let's look at a rule like this. So let's say that we know that two papers are the same. So if two papers are the same, well, then their authors are probably also the same. And this is something that we can very naturally voice in English, and then we can draw a picture and we can go to a PSL rule fairly simply. So once again, we have a situation like this. We have Plubis authoring Federalist number 1, and we have Alexander Hamilton authoring the first Federalist paper. And if we know Federalist 1 is the same as the first Federalist paper, then we can say, well, Plubis and Alexander Hamilton, probably the same person. So we can get a rule like this down at the bottom. Maybe hard for you people at the bottom to see, but essentially we have author of A1, P1. So here we have this link here, and author of A2, P2, that link on the right side. And if P1 and P2 are the same paper, then A1 and A2 are probably the same author. So pretty simple. And what you may be saying is like, okay, this works, but what happens if you have multiple authors? You're right, what if you have co-authors? That's not always the same. And in those cases, what you can do is you can perhaps maybe introduce something else into this rule and say, well, if they have to have like similar names, or their names have to be like, maybe you have a lower degree of similarity for the names. They have to have some sort of degree of similarity to be the same. And that's something you can play around with, and I'll leave that as an exercise to you, to kind of narrow that scope down more. But once again, our rules don't always have to be valid. They're allowed to be violated, so a rule like this might be able to help us. We'll see. Any other rules you can think of? No, this is a hard one. So we're looking at same paper, sure. Maybe we could do something with your, I guess not exactly your rule, but one thing it inspired me of was something with co-authorship. Maybe we could say or make some sort of, codify some sort of rule of if two people have the same co-authors, then they're probably the same person, or something like that.
Take into account how many co-authorships they have, like, so if you and I have like 20 papers in common versus some other people having one paper in common. Is it possible to quantify the frequency?
Yeah. Yep, you can quantify something like that. I don't have that in my slides, but yeah, you definitely can.
And all the co-authors of a single paper are distinct. You know that.
Oh yeah, that's a good one. We can actually put that in. That'd be a great rule to have in. All the co-authors of a paper are distinct. Unless there's some sort of clerical error, everyone on the same paper is different. Nice, that's a good one. But this is a rule I came up with for the slides. So what we're saying here is we pick up two authors from paper. So the top one, we'll let that be the author, we'll say that's the author, and the bottom one, we'll say that's the co-author. So in this example, we have James M. and Plubis, both being authors of the Federalist number 1 paper. And then we have Madison, Shea, and Plubis being authors of Federalist number 10. So if we can say, for certainty, not even certainty, but if we can just say, well, if Plubis and Plubis are the same person, then James M. and Madison, J. are probably also the same person. And of course, that's something we would surely not catch with a string similarity. Initially the first name versus the last name. That's a pretty hard thing to catch. Even like your best, even like a jar of Winkler, that's not going to catch something that different. So we can codify this as a rule, once again, if A1 is an author of P1, and A2 is an author of P2, then we have the co-authors, C1 and C2, being the authors of P1 and P2 respectively. Then, if the first co-author is the same as the second co-author, well, then those authors are probably also the same. The picture looks pretty complex, but you can see it's a very natural thing for us to want to express. If you have the same co-authors, it's probably the same person. Something like that. And so let's go ahead and see, let's go ahead and add these rules into our model. Let's see how our current model did. Ooh, our model's actually still running. That's pretty long. It's been running for quite a while, and it's still grounding out. So what happened? We can't really add in these new models until we fix this issue. Why did our model take so long? What happened? Like, we just added one rule, that one transitive rule. So, well, let's look at the situation. We only added this rule. Why would it take so long? Well, in this rule, what are we doing? We're kind of looking, are three authors the same? So to do that, we have to first, well, arbitrarily choose three authors. And recall that we have about 1,800 authors. And then we arbitrarily choose three authors from that set of 1,800. Oh, we got about 1 billion ground rules.
Jackpot.
Yeah, so we're going to have this transitive blowup because we have this very intuitive rule, but the number of ground rules for this is cubic in the number of authors we see. And that's pretty large. And that's one thing you have to be careful of when modeling, is you have to know, when I put in this rule, am I actually putting in a rule that's going to blow up my model? And transitive rules are very notorious for doing this because you usually have this cubic relationship. So what can we do to make this better? And what we typically do in PSL is a tactic called blocking. So blocking is the process of attempting to reduce the number of ground rules instantiated, or ground potentials instantiated, using some sort of computed heuristic. And in PSL, what that normally means is we'll compute some sort of heuristic, put it inside a predicate, and just add that predicate onto the rule. Now, you can kind of see the effect of blocking here. If we had some sort of squared relationship between the left side and the right side in this bipartite graph, then if we wanted to compute the full cross product between them, we would have something that looks like the graph on the left, this huge number of edges. But if we can somehow block and say, I'm going to take these references and I'm going to put them all in this little bucket, and instead of computing the cross product between all references, I'm only going to compute the cross product between everything inside that bucket. So then we get a graph that looks like the one on the right. Much nicer, you can see there's much less edges. And blocking is not a novel concept to PSL. It's been known under many different names in many different communities. Like blocks and canopies, typically for PGMs, chain trees, locality-sensitive hashing, block range index in database community. If we go way back, sorted neighborhood? Yeah, sorted neighborhood. So it's been talked about a lot. It's nothing particularly new. So before we go and get a concrete example of blocking, let's go ahead and I'm going to start the model on a different machine with blocking. Bring this over. There we go. So I'm going to start with blocking. I actually have a hidden file here that has the actual full model in it. So I'll do that and just a quick peek at the model. We'll look at it full later, but you see it has these rules and it includes some sort of blocking information. But I'm not going to show you because I'll show you later. But so let's go ahead and just run this. And let's go back and make sure it's running. Okay, good. And let's talk about a concrete example of blocking. So let's say we have a citation network like this, and we're comparing authors. So here I put two different authors, Adam Smith and John Adams. And we have 4 different references to each author, varying different names. Adam Smith, A. Smith, Adam S., A.S. And John Adams, similarly, we have that. And what we want to do with blocking is we want to introduce a partition into our graph, a cut in our graph, to eliminate all the edges along that cut. Essentially, we want to make 2 buckets in this example, one for all the Smiths, or the Adams, and one for all the John Adams. So we want to do something like this to make our graph look something like this. And once we have that, it's much, much easier to infer over. So what we can do in our rule, it would just look something like this. So on the bottom, we have the same transitive rule we've seen before, but on the top, all we do is we introduce our blocks. So we say we have this new predicate author block, and we say, okay, A1, author 1, that has to be a part of block B. Author 2, A2, that also has to be a part of block B. Author 3, A3, also make that sure that's part of block B. So when we compute these triangles, we say we're only looking at this transitive relationship between authors that are in the same block. They all have to belong to the same block, and then we'll compare them. So instead of doing it between the Adams and Smiths, we're only doing it within the top portion, and we're only going to do it in between the bottom portion. And if we extend this out to all the rules, we're going to get rules that look like this. And this is no big deal. You can just look at this in the model. So, but now the question is, how are we going to actually compute these blocks? Because we just kind of made the predicate and we said, it'll work. We put blocking, no problem. And when thinking about computing blocks, there's a lot of different things you have to consider. There's kind of this three-way trade-off between speed, precision, and recall. Now, speed is typically an important thing in blocking because a lot of blocking systems try to operate online. Now, in PSL, you don't have to. We usually pre-compute our blocks and just load them in as normal data, but a lot of the other kind of historical blocking systems try and compute it on the fly. So speed's really important for them. They want something that's fast. And then the other trade-off is between recall and precision. And for blocking, recall that we don't need to capture everything, or we don't need to make sure everything is 100% in blocking. We don't need 100% precision and 100% recall. Because all we're doing is narrowing down our comparisons to something that's more relevant. So we want a very high recall at the cost of precision. It's okay if our precision is low, because we're going to do the formal inference in our MRF later to actually get the real values. We just want to limit the number of comparisons we make. And then, of course, there's a bunch of other trade-offs that you can consider, like using blocks versus canopies, like overlapping versus non-overlapping blocks, the exact method you use, whether you do multiple blocking, so you maybe compare things in multiple different aspects, and you put them in blocks according to that. There's a lot of dimensions to blocking. But in this case, can anyone think of a more simple thing we would use for blocking? Can anyone think of, in our author similarity, in this specific citation example, how we may block these authors? What can we do to say, I only want to compare these authors that are in the same block? Can anyone think of anything? We got one right there.
A threshold of the similarity score?
Sure. We can compute the threshold of the similarity score and we say everything outside of this threshold, we're not going to compare to you. So that is slightly different in that is what we call pairwise blocking. Still definite form of blocking, but what we're going to try here is we're going to try and shoot for a bucket-based blocking, where we take all authors, put them in a bucket. But the threshold thing, that is a very valid approach, and that's actually more general than the bucket-based one in that you can always apply it.
So do you care more about the recall and less about the precision, because precision was going to be fixed by...
Correct. Yeah, so the question, I guess you had Mike, but do we care more about precision or recall? Typically we care more about recall. We want to make sure we don't miss examples at the cost of computing a little extra. And of course, I guess that also depends on your exact system. Again, with all machine learning, there's always a trade-off between precision and recall. You have to decide what's best for your application. But typically, in blocking, we prefer recall over precision. Can anyone think of anything else? How else can we look at these author names and say, immediately, I want to compare them or I don't want to compare them?
Initials?
Perfect. That's a great one, initials. We can just look at the initials for an author and we can immediately say, I want to compare these or I don't want to compare these. They have to match initials. So I'm going to augment that just slightly, and I'm going to say, we're going to take the initials and alphabetize them. That way, we fix the situation of last name first name first, things like that. Boom, you guys were so good, I have it right here in my slides. It's perfect, alphabetize initial. And this is a very common thing to use when blocking on author names, particularly in citation networks. So we can use alphabetized initials, and some pros on this, it's really fast. It's just some string operations, that's not a big deal. We can catch most misspellings, because most misspellings don't occur within the first letter of a name. We can catch cases where people are initialing on different parts of their name, whether they initial first, last, middle. We can catch different ordering, and we can catch a decent amount of nicknames. Like if someone named is Robert, if they nickname as Rob, we can catch that. If the nickname is Bob, we can't catch that. And that's part of the cons we see. If they have different nicknames, or if they author under completely different names. And you see that that's not an unusual thing for someone to choose. Maybe if they like non-native English, then it's not unusual for someone to choose an English name to publish under. That's a very common thing. And we don't catch those, but those are more rare occurrences. People will typically author under the same names, and it's really the initials we have trouble with. So we can do something like this, and if we kind of look at our example, using the alphabetized initial is the exact idealized blocking we were looking for. This cuts our graph exactly how we want to see it. So that's real good. So let's go ahead and look at, and that's how we have it computed in the example. So let's go ahead and take a quick look at our results. You can see that's the old one, still running. And our new one done. No problem. It finished, let's see, in about 2 minutes. 2 minutes, 10 seconds. That's pretty good. Pretty good, especially compared to our old one that's been running for, 10, 20 minutes now and hasn't completed. So we'll go ahead and look at this, and we'll take a look at the results in 1 sec. I have it compiled in a nice table later. I just want to, real quick, show you what our blocking file looks like. Resolution, and let's do author block. Something like this. So on the left we have the unique identifier for the author, and on the right, all we did for this blocking is just say, I'm going to compute the initials, and I'll let that initials be the unique identifier for the block. If we wanted to, we could make it an integer identifier as well, but in this case there's no real need to. So we just take all these people, put them in whatever block. Fairly simple. So let's go ahead and look at some results for this. So in terms of quality, this is what, on the top, we have what it looks like when we introduce none of these kind of transitive relational rules we worked on. No transitive equality, no kind of paper transitive, or no co-author transitive. Just the base model. And we see here's pretty much what we got before, 0.7996. We rounded up. And once we introduce, and then the three in the middle show when we introduce one of these rules at a time. So if we just introduce transitive equality, we see a boost of about 1.5%. If we just introduce the co-author one, we see a boost of about 1%. If we just introduce the paper one, we see another boost of about 1.5%. And then if we take all of these rules together as a full model, then we actually see a boost of about 4.6%. So we actually see introducing or having all the rules together actually was better than having each rule individually. So the sum of the whole was, in this case, was better than the sum of each individual part. And that doesn't always occur. We got kind of lucky on this model, but it's something that can definitely happen, and it's nice to see. So in results, we see something pretty good. And then if we're talking about results in terms of speed, so running not even the small one. Remember in this one we're running the medium example. Running the small example with one transitive equality rule runs for about 8 hours, and we stopped it. I think it ran out of memory on our 100 gig machine or something like that. For this one, the number of ground rules we'll actually see is about 220 million. And you might be asking, why do we not see the billion? Well, I guess actually this is the small example, so it has less data. But yeah, so even the small example with transitive rule without blocking doesn't even finish. Takes more than 8 hours. And then compare that to all the small, medium, large with all of our transitive rules and blocking. We see those finishing about 5, 3, and what is that? A little under not 5. About 1 minute, 3 minutes, and then we'll see in like 7 minutes or something. So we're seeing much this is to show that in PSL your models can be very expressive. You can have really powerful rules that capture a lot of these relationships, whether they're transitive or not. But you have to make sure to consider kind of the performance implications of when you do. And typically, we like to introduce blocking to handle a lot of those cases. Once we're able to introduce blocking, it kind of made available to us a lot more expressive rules. And there we go. That's entity resolution. Now you're pros on entity resolution. Any questions? We got one in the back. I think we're getting your mic.
So if you go back one slide, So it's fairly typical that if you look at the papers in the field, you see these comparative results, and you can go and find the CiteSeer database. What you can never find is the actual truth set that somebody's hand-coded, and it's
Sorry, the what?
the truth set, because I guess there is no ultimate truth set for CiteSeer. Somebody has to come up with it and say these are actually the same.
Yeah, we did. The truth data we got was. I'd have to look up the original paper this was from, but yeah, we're comparing it with. We as a lab didn't come up with these truth values. We used what they were using in whatever published paper. And I have to look that up. I can't remember which one.
Okay, so there is a published truth set, because I
Yes.
looked for it and never found it.
Yeah, there's a published truth set for this data set.
Okay, thank you.
Cool. Any other questions on entropy resolution?
We got 2 more minutes until lunch break. People are hungry.
Okay, so since we're real quick, I guess I'm going to blow through our conclusions. So we'll just say, okay?
Oh, you are going to do it?
Yeah, I'll just blow through them because we do not have the time.
It's fine. We started a bit late, so you got another 5 minutes.
Sure. Well, you give me 5 minutes. That's pushing it.
10 minutes.
Let's see.
People are hungry for PSL
Yeah.
more than cold.
Okay, so we have a couple concluding remarks. And of course all these slides will be available so you can just look them up there. And that'll be nice. So real quick I'm going to go through some kind of the additional problems we solved. In the beginning we talked about some of the domains PSL covered, but it's nice to see like really concrete examples of these. So another one, computing or trying to predict drug-drug interactions. This was a real good one because, so this one, it really showed a lot of the fusion Golnoosh was talking about, because essentially the rules where we were going to compute the similarity in different aspects, using different kind of similarity metrics. Is it chemically similar? Are the start effects similar? Are they like gene sequences trying to target similar? And then some really interesting ones are like, is the description in the World Health Organization text for this the same? It's like the taxonomy for this the same. So not even anything with like the chemical or biological nature of the rule, but looking at like the text descriptions for it. So essentially the model looks something like this, and then it just says, oh, if they're similar, then we're going to complete that triangle. If a drug and target is similar, and 2 targets are similar, then the drug probably interacts with that other target. So really simple rules like this, and it really shows the power of fusion. And my favorite thing about the paper was I think they listed like 10 drugs that they thought were going to interact, and 5 of those 10 have already been verified. And anyone in bioinformatics know, or in pharmaceuticals know, like trying to do research on drugs and humans and interactions takes forever. It takes so long to go through all the studies and human studies and whatnot. Oh yeah, so there's going. So here's the like the previous state of the art. Oops. And then the new, or then how the PSL model improved upon that. And then there's another one. That one before was by a couple people, including Dania Schreeder, and same, Dania also worked on this as well. This is predicting stance in online debate forums. So getting some sort of online debate forum and trying to infer who is taking what side in the argument. And as you know, you probably spent some time on the internet. That can be a very difficult task. And it's not a fun task. So something like that. And like the model, this is a very simplified version of the model. It has a lot more rules. This kind of shows at a high level what the rules are going to look like. Once again, you can see improvement. Another model, finding social spammers. So this isn't kind of email spammers. This is in a social network type setting, be it Facebook, Twitter, whatever. Can you find the accounts of people that are actually just spammers? And especially, this is really relevant in a lot of stuff today, but this work started before 2016. It was published in 2015, before like spammers and fake accounts became a lot more prevalent. So it's about detecting things like that. So this is about like using like latent aspects of credibility, trying to build up a latent model for credibility, and then talking about people being spammers. And then there's also some interesting social dynamics, like spammers tend to form social networks with other spammers. So if you can detect part of that network, you may be able to detect the rest of that network. So of course, improved over baseline. This is work by Peggy Koki. She does a lot of work in hybrid recommender systems, and she's published quite a few things at Rexis. So this is about using many different aspects of a user to make better recommendations. So not just using kind of user similarity or item similarity, but using things like the content of the item, the different social network for the users, demographics information, and fusing that all into a PSL model to make better recommendations. And I think we kind of go through those rules. But then she did some evaluation on Yelp and Last.fm, of course, see improvement over previous state-of-the-arts. And this is one, we wanted to spend more time on this one, but we don't, because it's a very interesting problem, but we don't have the time. So Jay Pujara, he ran AKBC at NIPS last year. He did a lot of work using about knowledge graph inference in PSL. So this is about taking a knowledge graph, usually a noisy knowledge graph or noisy pieces of knowledge information, and from those small noisy pieces of information, constructing a full knowledge graph. And this has a lot of aspects of, say, fusing data from multiple sources, overcoming noisy data, building these sort of relational rules, applying relational constraints for it. The specific model I'm showing is for the NEL, Never-Ending Language Learning project from CMU. And it's a huge knowledge graph, and they're constantly crawling the web, trying to extract small pieces of information and combine them into a huge knowledge graph. And those extractions are typically noisy, so it's about taking those noisy extractions, applying some relational rules on top of it, and then also applying constraints on top of it. Because NEL has some sort of types of constraints. Like they have a constraint that says a bird can't be a country. Sure, that makes sense. But they have a lot of these sort of rules like this, or this relationship is inverse to this relationship. So taking all of this kind of ontology and putting it on top of these noisy extractions to yield a better knowledge graph out. And yeah, so he did really amazing work with that. Here's more results he does later, beat state-of-the-art. A really interesting thing here is that not only did they beat state-of-the-art, but that was only on a subset of NEL that was limited to 2,500 facts. Running on the full NEL that had 4.3 million facts, the previous state-of-the-art couldn't do that. But NEL, or he's able to run PSL at a PSL through that in, I think what he has there, about a little over 2 hours. So pretty impressive. And then, so the main topics I want to talk about that we wanted to mention at some point, but we don't have time to talk about. Using temporal and spatial models, those are pretty interesting. Weight learning, of course, we talked a bit about weight learning, but like I said, you could do a full tutorial on weight learning. Structure learning, which instead of learning the weights for the rules, learning the rules themselves along with the weights. Of course, a much, much more difficult problem, but something that we're also working at currently. Causal modeling, trying to figure out the cause of some relationships. Dania, once again, put in a lot of work on that. Lifted inference, Golnoosh has worked on that, and the person Sharam, who's left, is also starting to try and work on that. Kind of doing more efficient inference by lifting. Fairness, Golnoosh is really big into fairness, making more fair models, and not like fair from a mathematical and statistical standpoint. And then doing actual decision making using PSL. I think yeah, that's about it. We have some highlights of those, but I don't think we have time to go into go deeper into each of these specific topics. I think that's about it.
Resources at the end.
Oh, resources at the end. Thank you. So we have.
Yes.
Here we go. We got some resources. Takeaway. Resources, like I said, at the links website, or the PSL website, psl.links.org, you can find pretty much links to pretty much all of this sort of information. You can find information about our lab, links including all of our publications at just links.org. D3, the kind of data science institute that we are working under, where we get to work with a lot of other really great companies. You can find information about that there. You can find, there's a kind of the primary PSL journal papers right there, but like I said, you can also look at all of other publications. And this is more links to our different code things, our main repository, development repository, the PSL examples repository, things like that.
There's also a NIPS tutorial from last year.
Yeah, we had one from the year before, and Jay gave one at Star AI. He gave a great knowledge graph inference tutorial as well that involved PSL.
Are those links on both sides?
Yes. Yeah, we'll give the MLTrain website.
So on MLTrain
slides.
I put all the presentations, but if you go to the PSL website, everything is there. You can find everything on the web. Like even if you go to the slide and search it, you will find it.
Are you going to make the slides available, Eriq?
Yeah.
They're already available.
Oh,
Yeah,
they're already out.
available on the MLTrain website.
Yeah.
The last one